In this video, we'll analyze the relationship between the statistics at the input and at the output of a linear system when we have a stationary random process at the input, but in the frequency domain. In the time domain, we have the relationship between the mean at the input and at the output, the autocorrelation function at the input and at the output, and the expressions for the cross correlation between the input x of t and the output y of t. Now we are going to analyze these same expressions in the frequency domain. In the time domain, the mean of the output random process, the mean of y, is equal to the mean of x times the integral of h of t. The integral from minus infinity to plus infinity of the impulse response of the linear system. Taking into account the properties of the Fourier transform, to integrate in a domain is equivalent to evaluate at zero on the other domain. And this means that the mean of the output process y of t is equal to the mean of the input process x of t times the frequency response of the linear system h of j omega evaluated at omega equal to 0 radians per second. With respect to the power spectral density, the power spectral density of the output process is given by the Fourier transform of the autocorrelation function of the random process, because the random process y of t is an stationary random process. In the time domain, what we have is the convolution between the autocorrelation function of the input process, h of tau, and h of minus tau. This is equivalent to the convolution of the autocorrelation function of x with the time ambiguity function of the input response h. Convolutions in the time domain become products in the frequency domain. The Fourier transform of the autocorrelation function of x is the power spectral density of x, and this is the Fourier transform of h in the frequency domain, and the matched signal has the complex conjugated response, or what is the same. If we have the time ambiguity function in the time domain, in the frequency domain we have a square modulus of the frequency response of h in this case. And because of this, it's straightforward to see that the power spectral density of the output process y is equal to the power spectral density of the input process x times the square modulus of the frequency response of the linear system, square modulus of h of j omega. For the crossed statistics between input and output, it's possible to introduce the definition of the crossed spectral density between the input and the output as the Fourier transform of the autocorrelation function between the input and the output. And the same thing can be done for the cross spectral density between the output and the input. In this case, the cross correlation between the input and the output was given by the convolution between the autocorrelation function of x and matched h time reversed. Fourier transform of this, power spectral density of x, Fourier transform of this, complex conjugated of the frequency response of h. And here we have this expression. Cross spectral density between input and output is equal to the power spectral density of the input times the complex conjugated frequency response of the linear system of h of j omega. And equivalently, for the cross correlation between the output and the input, which is equal to the convolution between the autocorrelation function of x and the impulse response of the linear system in the frequency domain, Fourier transform of the autocorrelation function is the power spectral density of x, and here we have the frequency response of h in the frequency domain. Here we have the corresponding expression for the cross spectral density of y and x is just equal to the power spectral density of x times the frequency response of the linear system. Obviously, because of the definition of the cross spectral densities, the cross spectral density of Y and X is equal to the complex conjugated cross spectral density of X and Y, as it can be seen in these two results over here. And here in this diagram, we represent the relationship between the different power spectral densities. Here we have the product of the power spectral density of the input process X times H. This provides the power spectral density, the cross spectral density between the output and the input, times complex conjugated frequency response of H. We have the cross correlation from the input and the output, and times the square modulus of the frequency response of the linear system is providing the power spectral density of the output. And it's possible to see some additional relationships to change in the cross correlations X, Y by Y, X is just a complex conjugation, and here we can have the expressions of the power spectral density of Y in terms of the crossed spectral densities. Straightforward relationships, just the product with H or with complex conjugated H.